Hi students, in this video we look at the derivation of impact stresses, something that I couldn't do in live classes. So I thought I will record this and upload it so that you can go through the derivation. And let's move on to the next slide. Okay, so this slide you would have seen, okay, in my explanation of what is meant by impact stresses. I had shown this. Right? By impact stresses, we mean stresses that are induced due to suddenly applied load or instantaneous loads. Examples: hammers, hydraulic presses, crash guards, and so on. All right. Now, what we will do is we will look at two things. One is we will try to theoretically understand what is the impact of suddenly applied load and its induced impact stresses when you will compare it with a stress induced due to gradually applied load. Okay, how does the stresses vary between both the cases? We will mathematically understand that, and then we will go on and derive the impact stress formula. Okay, those equations which you have used from your handbook, how do we derive it? So we will go through the derivation process. All right, so let's go on to the next slide, or in this slide itself let me just explain the figures. uh, what is seen here is this is a case where a load W is acting on a bar of length L. Okay, and in this figure A, the load is very gradually applied. That is, this load W is very gradually placed on the area, on the sectional area of the bar. Okay, and because of the weight, the because of this gradually applied load, the body deforms by delta st, or what is known as static deflection, right? And you have learned in mechanics of materials that static deflection can be obtained by pl by ae, or wl by ae in this particular case. And if you look at the second figure here, this is a case of suddenly applied load. That is, the load of weight W is dropped from a height h, and as a result of which this bar is undergoing a deformation of delta st plus delta, right? Therefore you can see that there is an additional deformation when you will check it with gradually applied load. Okay, therefore it will be static deflection plus a certain deflection due to like impact. Okay, so this is how impact deformation happens. Okay, let's move on to the next slide. Okay, now here, see, I have not really typed out the matter here because it takes a lot of time writing these formulas and equation using PowerPoint. So I've just copied and pasted matter from my notes here in directly, and I hope it works for you. All right, so what we will try to do is we are going to check the impact of instantaneous load versus gradually applied load. Okay, so let us define the variable W as the suddenly applied load. Okay, say in Newton. Delta is deformation due to suddenly applied load. The total deformation due to suddenly applied load is denoted by the symbol delta. E is modulus of velocity, area is A, length of the member is small letter L, and sigma suffix I is the impact stress induced due to the sudden load. Okay, now what happens is, because of the application of this impact load, there is a deformation. It's a deformation that has happened. Therefore, what is the work done? Work done, we know, is force into distance, isn't it? The force into the deformation that is induced, right? Therefore, the work done will be W into delta, right? This is the work done, Newton mm. All right. Now, what happens is the load when it acts on the body, and as the body deforms, the energy will be stored in the body as strain energy. Right. Now, if you will look at this figure here, okay, if you will look at the figure, this is a graph of load versus deformation. Okay, along y-axis you have load, let me denote it as P, and along x-axis you have deformation. All right. Now, for our case, when the load falls on the body, and if you will, from zero load to the maximum deflection of delta, okay, if you will draw the sketch, all right, if you will draw the sketch, okay, this much is the load that is acting, P, okay, and the deformation of the body is delta. Right. Now, if you need to know what is the strain like energy, or the energy absorbed by the body when the impact load is acting, you need to measure this area. Okay, area under this right angle that you see, area under this triangle that you see, will give you the strain energy U. Right. Now, what is area of a triangle? Half into base into height, isn't it? Therefore, you can see that U is equal to half into base into height. Right. Half into P. P is the impact force. Delta is deformation. Right. Therefore, half into P into delta will be the strain energy. All right. Remember to understand the difference between W and P. W is the load. Okay, W is the load and P is the impact force. All right. If if the load was gradually applied, then the load and the force would have been same, right? Whereas since the load is suddenly applied, the force that is experienced by the body is greater than the load, okay, which is denoted by P, right? Therefore, strain energy is half into P into delta. All right. Okay, so let's move on to the next slide. Now, here's I have explained what is P. P is the force at which deformation delta is produced. All right. So strain like energy is half into base into height, which was half into delta into P. Right. Now, P is the force. Okay. Now, if I denote sigma I as impact stress, okay, impact stress is nothing but load by area, isn't it? Right. Therefore, load P, I can rewrite it as stress into area, impact stress into area. Right. Now, this is what is shown here. Right. Instead of P here, I have written sigma I into A. Okay, this is still strain energy, half into sigma I into A into delta. Okay, now what is delta? Delta is deformation, isn't it? Deformation or change in length. All right. Now, what do you mean by strain? Strain, we know, is change in length to the original length, isn't it? Right. And what is modulus of elasticity? Modulus of elasticity, according to Hooke's law, is stress by strain. In this case, it is impact stress divided by strain. Right. Therefore, what we can do is we can replace this delta as stress into L by E. Okay, stress into L by E, which is basically from this equation here. Right. If I will substitute strain as delta by L and replace it for delta, you will get delta as equal to sigma I into L by E. All right. Now, that is what is shown here. All right. Now, simplify it, and you will get strain energy U as equal to half into sigma I into sigma I becomes sigma I square A into L divided by E. Alright, so this is the strain energy. Now, when a load, see, if I will take this as a body here, fixed at, placed at the bottom, and you have a load being dropped of W, and it has deformed by a distance delta here, alright, because of the load. Okay, now we'll know that when the load impacts here, the body will absorb like energy, which is known as strain energy U. All right, now and the strain energy will be equal to the work done in deforming the body by delta. How much was the work done? Work done we like know is force into distance, right? Therefore W into delta is equal to the work done, right? And strain energy is half into sigma I square AL by E. Okay, now both strain energy absorbed by the body and work done in deforming the body by delta should be equal. Therefore we will like equate both. Okay, equating strain energy to work done, if you will simplify that, you will get sigma I is equal to 2 times W by A. Okay, now what is W by A? W by A is stress, nominal stress. Okay, that is stress induced by a load, the W, right? Therefore we can see that impact stresses is 2 times the stress induced due to gradually applied load. Okay, therefore the effect of impact is 2 times the effect of normally applied load, right? Therefore, and this holds good for deformation also. Okay, if delta I is the total deformation, then it will become 2 times deformation due to gradually applied load. Or if I put delta I as deformation due to impact is equal to 2 times the delta, right? And that is what is saying here. Suddenly applied load is equivalent to twice the static load. Okay, stresses induced due to suddenly applied load is equivalent to stress induced due to twice the static load. Okay, so this is the effect of impact stresses. All right, so let's move further. Now let us derive an equation for impact stresses. Now those equations which you have taken from your handbook and used to solve the problems, we will see how we get that a formula for impact stress. Okay, so this is a very similar figure. You have seen it. A load W acts upon the collar that is fixed to a beam. Okay, and this beam is of diameter D, right? And the total deformation due to this impact of the load falling from a height h is delta, right? And P is the force that will cause a deformation delta. Okay, which will be static deflection plus deflection due to impact. Okay, now static deflection we know is PL by E, WL by E in this particular case. Okay, so let's look at the uh, derivation here. Now this is more or less the same figure that I've entered in my notes. Right, delta I is the total deformation, height is h, and L is the length of the bar. All right, now let's look at the deformation now. Okay, now what we are interested in is finding out an equation for delta I, which is impact stress induced in the bar due to impact. Now this is what we need to find an like equation for. All right, now again, as we have seen before, the total work done by the falling body is equal to the change in potential energy, isn't it? In the sense, since we are dropping a load. Okay, now we have a load here. This is a cantilever beam, and this load is falling from a height h, right? Therefore initially the load has got a certain potential like energy, which gets transformed into kinetic energy as it falls down, right? Now what is the now when the load impacts the collar and the collar gets deformed, or the beam gets deformed by a distance delta, right? Now, what is the work done? Work done is load into total the distance. Okay, that is the potential energy of the load at an height h is equal to W is equal to W into h plus e dash, right? Or W is equal to h plus maximum deflection delta max. Okay, this is the total potential like energy. Okay, now this like now when the load strikes the body, this total potential like energy is absorbed by the system, right? Therefore, uh, half into P into E, okay, is equal to half into H plus E dash, right? That is work gained by the system. Okay, now this is again similar to what we have seen the previous figure, strain energy, right? If I will draw a graph between load and deflection, right? Initial the energy gained by the system is half into P into E dash, okay, and the energy with which the body hits uh, the load hits the body is W into H plus E dash. Okay, now we know that force is equal to stress into like area. Okay, and deformation is equal to stress into L by E. Okay, so substituting that and equating both, we will get a quadratic equation, right? Now, solution for that is half in is minus b plus or minus root of b square minus 4ac divided by 2a, right? Now here b is w minus wl by e, a is half sigma square a by e, and c is minus w, right? Therefore you substitute that and simplify it, right, and you will get an equation for stress. Okay, now you take only the positive sign here because stress is a positive, because a negative sign only like indicates the direction of load. Okay, therefore if you will take the positive sign here, you will get the formula for stress as this value here. W by A is actually static stress. Okay, now this is the same formula that you have in your handbook. Okay, this is the same equation that you have in your design data handbook. Okay, now this is for stress. Similarly, you can also obtain for uh, deflection also, same equation. Okay, and that same formula will hold good for bending and torsion also, right? Now when we speak about torsional stress, instead of delta st we'll have theta st, because torsional deformation is angular. Therefore you will have theta st here. This is delta st, right? Other than that, the equations are more or less same, and all these equations are there in your handbook. All right, it's there in your handbook and you have already used them to solve problems. Okay, all right then. So that is what I wanted to inform you, and I have also included the handbook here so that you can refer. And if you are aware, I have also uploaded it in the Google Room for those who don't have a handbook with them. All right. Okay then. Thank you. Bye bye.